So, hello everybody. My name is Ilan Godik, and today I'm going to talk about optics with Monocle, modeling the part and the whole. So, a bit about myself. I'm a CS undergraduate at the University of Haifa, and I've been contributing to the Monocle library from very early on in its development. So, what are lenses? Monocle contains different abstractions such as lenses. So, lens basically in the simplest model is just a getter function and a setter function for an immutable object. Okay? So, with a lens from an S to an A, we can get an A inside an S, and we can set a new A to be inside the S. All right? We can set it. So, let's look at the classic example, which is updating nested records. So we have our model, which has a person with a full name and address. An address has two fields, which are city and a street, and each street has a name and a number. So say we have a person, and we want to update the name of the street which he lives in, and we want to capitalize it. So with vanilla Scala, we can, there's the copy method, with which we can only modify one field and copy all the others. Because with the mutable objects, we must copy all the other fields. All right. So here we copy the address field with the old address, change the street, copy everything in the street, and change the name and capitalize it. Okay. This is what we have with vanilla Scala. And it's really a lot of code, and I don't know, it's not nice. So with Monocle, we can define lenses once for each field in a case class. Here we do it with a lenser. For example, the address lens is a lens from a person to an address, and a street lens from an address to a street, and a name lens from a street to its name. All right? And at the user side, we just compose the lenses, all right? Address compose, street compose name, and modify it with a capitalize function. All right? We can get it even shorter with macros, the macro annotation. We can just annotate it with the lenses annotation, and it generates all the lenses in the companion object. It's IDE friendly. IntelliJ does recognize it. It's very nice. It's much shorter. And the user side is just composing everything with a one-liner. So here is our object graph. All right? We have a person with all the fields, with an address, city and street, and the street has a name and a number. Let's look at the height of the tree, of the object graph. So with vanilla Scala, our code grows in proportion to h squared, because we copy everything every time, because we need to write out all the path. And with lenses, the code grows only according to h, to the height of the tree. All right, so with lenses, we just go one step each time, and we do not need to copy every subpath on the way. For a bit of intuition in what direction can we compose lenses? All right. The nice thing about lenses is that we can compose them any way we like. So every path we go through the arrows, we can create a lens. So we just need to follow the arrows. For example, we can create a lens from a person to an address to the city, or a person to an address, to street, to name, whatever we want. All right. Any questions up to now? Nothing? All right. So how do we compose lenses? So as I said before, we compose them just by following the arrows. So with the lens of an S to an A, and another lens from an A to a B, we can create a new lens from an S to a B. All right? So how can we get a B from an S? We just access the first one and access the second one. That's the easy one. And given a new B, how can we update that B inside the original S? So what we do is at first get the A inside, all right? We set the new B inside the new A, and then put the new composed A inside the original S, all right? We get the A, put the B inside, and put the new A inside S, just how we did with copy.
When you say inside S, do you mean like S doesn't change?
Yes. We create a new S, yes, using the lens S2A. With the lens S2A, we can set an A inside a B, inside an S. With the lens AB, we can set a B inside an A. All right, so we'll take these steps, and in order to access deeply in the structure. All right? Everyone following? Good. So let's try to push the limits of lenses. So here's an interesting question. Can we change the type of what we are working on and setting a value? During a set operation, can we change the type? So here we have a tuple of two integers, all right? 1 and 2. And we set the first field to hello, to a string hello. And we want to get a tuple of a string and an int. So it's possible, and we just extend our lens definition to 4 parameters, all right? So a p-lens, polymorphic lens we'll call it, all right? With a polymorphic lens of SCAB, we can get an A inside an S, and given a new B, we'll create a T with a B inside. Let's look at the previous example. For example, the S was to a pair of integers, and the A was the first integer. The B was the string hello. The T was the pair of a string and an int, and here's the string hello inside. All right? So let's look at an example. Yeah?
Can you go back one slide?
Sure.
How is the T inferred? There's nothing there to get the T inferred. If I set B and S and I'm getting a T back.
Yeah. You define the lens. You define the lens from something to something. So for example, with the tuple, at the call site when we set the new string hello, then it gets the T. All right. So let's look at the example of unit conversions. So we're given 2 lenses from meters to centimeters and from meters to millimeters. So what do these lenses do? The nice thing about lenses and all the other optics is that we can look at the same data from different perspectives. So for example, we have 5.5 meters, all right, 5.5. And then we can say we want to add 10 centimeters. Then we get a result of 5.6 meters. It's just looking at the same data from different perspective. All right? So the question is, can we create, given these 2 lenses, a lens from centimeters to millimeters? What do you think?
Activate twice from meters to centimeters and once again.
Say, let's say these are different types, not just integers. We can't just manipulate it like that. All right? So the answer is we can't, because there is no path from centimeters to millimeters. We need to follow the arrows. So what if we had a bidirectional lens, all right? That we can, that we have lenses on 2 sides, all right? It's called an isomorphism, all right? Just lenses on both sides. So here we can make a lens from centimeters to millimeters by going from centimeters to meters and from meters to millimeters. Right? We can compose now because we can follow the arrows. All right? We can view isomorphisms from another side, not as lenses, but as a bijection. A bijection is just a function with an inverse. All right? So say this is our function from A to B, all right? And, and for every element of B, we have an inverse function that takes us back from a B to an A to the same value. All right? So in set theory or something like that, you can, when you have a bijection between two sets, we can say they have the same size, or a cardinality is called. All right? But if we don't have such a nice correspondence? Okay, not everything is equal, say. So this is what we call prisms, that we have some values of A that don't have a target. All right? But a subset of A does have a function and an inverse. All right? So let's look at an example. Say A are strings and B are ints. So we have the string hello, it doesn't have a target. The string 50 goes to 50, right? And we can go back from every integer to a string. For example, 42, we get the string 42. All right? So we have two functions. One from an int to a string. All right? We can always get from an int to a string. But from a string to an int, we can't always go. All right? So we either get a none, which says we do not have an answer, or we get a sum that we do have an answer. So there are a couple of laws for prisms. There are laws for lenses and isomorphisms too, but I want to mention these. The first law says that if we have an answer, we can go through, for example here we can't, if we can go through, then going back must yield the original value. All right? Just like the diagram. If we have an answer, going back must give the same answer. And if we go back from B, we must be able to go back to B. All right? If we go from here to 50, we must be able to pass 50. All right? So if we have laws, we can do property testing. And with a Scala check, for example. Who knows about Scala check? Very nice. So say we have this implementation. Just string to into string, just to string on object, and string to option of int. We try to do to int and catch the exception. If there is, we get none. All right? So the nice thing about property testing is that the framework generates lots and lots of values for you and tests the properties if they hold. So turns out that this strange thing, if we do toInt, we get 9. Like, what? So it's just in a different language, 9 or something. So it violates the first prism law, which says that if we have an answer, going back must yield the same. But here we went to 9, and going back gave us the string 9, not the same.
There are simpler examples with this. The string 050 maps to 50,
yes.
But 50 doesn't map back.
Right.
Can you please repeat the question?
So he says there's a simpler example that 050 maps to 50, but 50 maps only to the string 50. So yes, with prisms we would not like that to hold. All right? For example, plus 50, we can think of it as 50, but still it doesn't go back. But minus is okay. All right? So property testing is nice for checking properties. Let's see an example with prisms. Say we have a user interface with two fields, and we want to convert both ways between Celsius degrees and Fahrenheit degrees. All right? So we need to pass them because they are given in strings. They are just text fields. So we have a prism from string to Celsius, say into something, whatever you want, and a prism from string to Fahrenheit, and we have an isomorphism. Just we can go both ways between Celsius and Fahrenheit. Okay, so we can go from Celsius to Fahrenheit and from Fahrenheit to Celsius. So if we compose the optics from the left, we can go from string to Celsius and from Celsius to Fahrenheit, and we get a prism from string to Fahrenheit, which we can bind to this field. And it will handle all the errors. And also, if we go from the right, we can compose also from string to Fahrenheit, from Fahrenheit to Celsius, and we get a prism string to Celsius. And we can bind it on the left field. All right, everyone with me? Good. So let's look about, a bit about some theory behind lenses. We start with a question. Can we unify all the lens functions into one representation? So we have the basic lens functions, get, set, and modify. Modify takes a function from A to A, what's inside, and modifies the S. All right, given an S, it modifies the inside with the function. We will look at two other examples, which are modify maybe, which takes a function from A to option of A. It might fail the computation inside. And it takes an S and yields an option of S. If this failed inside, it will fail outside. And if it succeeded, we'll get a sum here, right? And it will modify the inside. And another interesting one is modify list, which takes a function from A to a list of A's, all right? And takes the S and then returns a list of S. So it gets the A inside and applies the function. We get a list of A's. And for every element inside the list we get, we'll set one value in the S's. So we'll have a list of S's, which corresponds to each value we got from the list. All right? So I'll have to cover a little thing here, which is called a functor. All right? Functor, you can think of it as everything that has the function map. All right? It has to abide to some laws, but it's good enough for now. So the function map, what it does is, given a function from A to B, it needs to turn an f of A to an f of B. Let's look at examples. So, everyone with me? Yes? Good? Good. So, let's look at the functor for list. You know this, just a function map on lists, right? From the standard library. So, for example, we have the list 1, 2, 3, and we give it the function plus 1. We'll get back the list 2, 3, 4. It applies the function to each element. All right? And let's look at the option function. All right? Given a function A to B and an option of A, we want to give back an option of B. So we'll look what is the option that we got. And if we got a none, we have no way to get a B back. All right? So we must return none. And if we got a result, a sum of A, we'll just apply the function f inside the value. All right? Everyone got it? Good. So the answer, how do we model all the lens functions in one signature, is this. All right? If we know that f has a functor, for example, option or list, all right? This is the signature. Given a function a to f of a and an s, we give back an f of s. I'll show a lot of examples so you will understand it. All right? So the last two really look like this signature, right? We just take f and substitute option into it, and we can take the f and substitute list. All right? But how do we model all the other functions, right? It doesn't look similar, right, at first. So it turns out we can. So let's start with modify. All right? What we can do is think as f as a type level function, which takes a parameter, a or s, for example, and gives back another type. All right? So here we will take the identity function, that for every a, we return an a. So we'll substitute f for identity, all right? And we get, given a function a to identity of a and an s, we get back an identity of s. We'll substitute the value of the type synonym. It's a to a. Given a function a to a and an s, we get back an s. And that's just the signature of modify, right? We can change the value inside and it changes the s, right? So what we need to show that is that identity has a functor, as we showed before, all right? So here's the what is functor. We need to have the function map, and let's define it. So identity of a is an a, right? And we want to define a functor of identity. So given a function a to b and an identity of a, we need to return an identity of b. We can substitute it, all right? Function a to b, given an a, we need to return a b. And that's just applying f to the value we got, all right? So the map function for identity is just applying the function to the value we got. All right? Everyone here? Good. And let's see how do we do the other ones. So the function map is easy. We just modify, ignore the value, and set what we want. So for example, we want to set a specific value, all right? And modify gives us what's inside, and we don't care. We just say always put this inside back, all right? But how do we get this signature from this? Because the A here is on the right verse, and here all the A's are on the left. How in the world am I supposed to turn this into this? So again, we can think of the f as a type level function. And the idea is that we want to capture the a from here and put it here. So we want to turn this f of s into an a. All right, so what we'll do is use the constant function that given any value, it ignores it and gives us the value we want. All right, I made up some syntax here, curried parameters. All right, in Scala it's not very nice, but just to demonstrate it here. So we'll take f as constant of a. We want to replace all the f of something into an a. All right, so we'll substitute it. We get a to a constant a, right? And an s to a constant as. All right, so we can substitute it further. Remember, constant of x and t is just the first type. So constant of a and a is just the first a. And constant of a and s is just an a. All right? Now we got an s to an a, and this we don't need. We'll just put the identity function here. Just get rid of this. And now we got our s to a function. All right? So get is just a lens with a functor as constant of a, and with the identity function. That's all. Yes?
I understand the point of lenses when you're talking about setting and modifying.
Yes.
Why do you need a get? Why do you need a lens to get? I can get anyway.
Yes.
Is it just
So
a theory?
Yeah. Yes. So he asked, why do you need a get in a lens? Why can't I just use set and that's it? So the idea is that in order to compose lenses, we need to know what is the getter. Because if we, in the start, we looked, I'll backtrack a bit. Sorry. Oh God. At the very start, all right? In order to compose lenses, we needed to get the A inside. We need to get the A in order to set inside. All right? So it comes as a combination. We can't do one without the other. All right? Good. All right. So we showed how we can substitute const, and now we need to show that it's a functor. All right? So this is what we have. Const xt is just x, and we'll provide a functor of const x, right? And it takes another type parameter in the function. So given a function a to b and a const xa, we need to return a const xb, right? The a comes here and the b comes here. If we substitute the const again, we just get the x, the first parameter, right? So with the function ab and an x, we must return an x. We have no other way of returning an x but returning what we got. No other way to create an x value. So notice here we really just ignore the function f. We do nothing with it. We have nowhere to get an a from and nowhere to get another x from. By the way, this is called parametricity, that the amount of implementations is limited because of the type parameters. Because we are quantified, we say for all types A and B, we must be able to implement this. So because of this, there are really limited amounts of implementations we can do. And this is good. All right? So we showed how to implement all the Laarhoven functions: get, set, modify, and modify maybe, and modify list. So let's look at how we can create this type signature at all. All right, we have some weird type signature. How we can implement it with specific lenses. So I marked here in purple the original getter and setter. Okay. We have, for example, get the first value of a tuple and set the first value, for example. All right, so we are given a function a to f of a and an s, and we must return an f of s. So we'll start by getting the value a from the s. Right? Remember, with the lens, we are given here that we can get from an s to an a. All right, we get an a from a get s. Then apply the function f. All right, we have an a, put the a, and get the f of a back. Remember that f is a functor, which means we have the function map. All right, so the function map here is of the type given a function a to s, where an f of a will return an f of s. Right, so we need to provide these functions. Only this one. This is the f of a we have here. So what is our function a to s? It's just setting the value a inside. All right, given an a, we set inside the original container the value a. That's all. So we turned our f of a into an f of s. Okay, all of this is f of s. For the next slides, I'll write it more shortly. Lens with the function f and s, we apply the f of get and map it with a set. Right? So let's look if what we implemented before, the derived get and set from the van Laarhoven type for lenses, gives us the results we want, get and set. All right? So let's look at it. We'll start with modify. All clear up to now? Everything good? Yeah? All right.
It's challenging.
All right. I could repeat it afterwards. All right. So we want to see if our implementation, the derived get and set that we got from here, is the same as the original get and set. All right. We'll start with modify. We'll show you it is the same. So remember how we did modify. We just put f as identity. So we have the now we substitute identity for f, right? We get this signature a to s to s. All right? And this is the implementation I showed in the previous slide. Okay, f of get and that's it. So what happens here is now f is of type a to a. We substituted this f into identity. Okay, so we just lose the f everywhere. So now the get S is an A, and f of get is also an A, right? This is the modify function. And then, do you remember what the map function on identity is? The map function on identity is just applying the function to the value, all right? The map on identity is just applying the function on the value. So the function is setting a value into the S, all right? So if we apply the function to the value, this is our value. So we get this set of the value with S, right? Set of f of get. We get it, apply f, and set it back. That's modify, right? That's correct. And set the new set, the derived set, I mark it in yellow here, is given a value we want to set inside and the original state. We invoke modify, ignore the value, and always return x, right? And what we get is here. The f here just ignores the value inside, right? It ignores the get, and all this f of something turns into an x. So what we get is set x with s, the original set in purple. All right? If you have questions, please ask. Really. I'll repeat it. And let's look at get. Do we get the same result? We have a constant of a and x, and we return an a, as you remember. We take the f as const a. This is our signature. Turn every f into an a. All right, this is the signature we get. So here, what happens is we get the value s, get the value a from the s, and apply the function f to modify it. All right. And then remember what is map on const. We ignore the function, return the same value. So this whole function, we just ignore it. Okay. So what we're left is f of get. And this takes this function, right? And we wanted, and we put identity there beforehand, right? So we'll put identity here, which means we just get the get of s inside. So the new derived get is just the old get. Okay? So this was a bit of theory. So yeah, there are other models for lenses and prisms, optics, all of these, which are very interesting. For example, the pro-functor model and others. Maybe next time we'll present about it. Yeah, great. So, good. So, a bit about the library, Monocle. So, it provides a lot of built-in functions and optics. For example, accessing a key at a map. Maybe it is there, maybe it is not. JSON, for example. We don't know the structure of JSON. It's just text, right? So we must assume some structure about it, which it has, and then work on it. So for example, if we have an object, we assume it is an object and we continue working on it. This is the reason. So Monocle provides useful macros for defining lenses. All right, for example, the lens annotation, creating lens, as I showed at the start. The main benefit is the classic example that if you want to update an nested record, you can do it nicely and shortly. All right. Monocle used different models over time for lenses. For example, the model we saw in the start, just a getter and a setter, or the polymorphic lens that we can change the type in the middle. And now it uses a combination, a hybrid between what I showed you in the start, P-lens, and what I showed now, Van Laarhoven. Because Van Laarhoven are really good because you can modify very efficiently. For example, with the classic model, if you want to modify, you need it first to get the structure. You go in, then go out, get the value out. Right now I want to set it. I go in again, set it, and get it up. All right, and construct every S on the way. And with the Laarhoven lenses, you can just go inside, apply the function, and construct it back on one go. Right? And we do also some benchmarking on all the lenses and all the things in the Monocle. And it turns out that currently it's quite good, the performance, really good. It's just bottlenecked by function values in Scala. They aren't the fastest, but that's what it is. All right? So, here are some resources if you're interested. And thank you. Yes, please.
You mentioned playing with JSONs.
Yes.
Do you mean like you can somehow describe what the JSON structure is? Is it similar to PlayJSON?
Yeah.
Format, something like that?
Yes. So he asked if what we can do with the JSON with the prisms and lenses is similar to existing JSON libraries. All right. So what we can do with the lenses is really modify. We can at first use it with the JSON libraries because it doesn't parse them. Just say we have an AST of the JSON, all right, and we can just convert it to the structure you want, because JSON is somewhat unstructured. Every step, every object can be either an object, an array, a string, a number, right? So you assume the structure and can work on it. You can modify the JSON, really go deeply and modify something and construct everything, or go to your model. For example, lately in the Argonaut library, they added Monocle lenses to work with JSON. So that's a point. Anyone else? Yes.
A bit of a general question.
Yes.
You said you're from the beginning, from the first step of the Monocle library. When you start to develop a library like that, how do you know about the one?
Yeah. So
how do
first
you combine the theory with the?
Yes. So the question was, when you start to write a library like Monocle, how do you know about all this theory, for example, Laarhoven lenses and all that? Just as a disclaimer, I did not write the library. It's Julian, truth note, right? Yeah. So there is a library lens in Haskell, all right, by Edward Kmet. And there are different articles about this and all the different models and all of that. So kind of a lot of accumulating knowledge and trying out different models to see what's best. All right? Any questions? Any more questions? Yes.
There are also other lenses libraries like Scala Z has one.
Right.
What are the main differences?
So what was asked is there are different lens libraries. For example, Scala Z, there's also a shapeless lens library. All right. So what is asked is what's the difference? So all the lenses libraries use different models for lenses. So there is the co-state, common, co-algebra model. There's the simple model. There's the Van Laarhoven model. There's the profunctor model. So Scala Z uses a different model. And actually, what's planned is the Scala Z lenses will be deprecated over time, and everyone will move to Monocle lenses. Also, Julian benchmarked all the libraries, and turns out that Monocle is really, really better at performance. All right? Any more questions? Anything? Okay, thank you.
Thank you.